So that's the radical. If you put something out in the front of it, like 4, that would just be a coefficient. Just like it is if we say 4x, it's a coefficient. Now the number inside of here, next to the radical, like that small number, kind of looks like an exponent. That's called an index. So that's definitely something that you guys are going to want to know what an index is. That just tells you which root you're taking. Right? Normally we take the square root, so we need 2 of something in order to be a square root. With a 5th root, you would have to have 5 of something in order to take a 5th root. Okay? And then the number under the radical, that's called the radicand. That one's not as important to know, but you guys will definitely need to know what an index is. We're going to be talking about that a lot. Okay. So just some little bit of vocabulary here to start off. Again, the check mark symbol itself is called a radical, so then we call like all these groups of things, these are all radicals, but they are different types of radicals. Square root, which means I need to have 2 of something in order for it to come out. So as we do that SOC method, which is my preferred method of simplifying radicals, 2 times 22 was take the smallest number out, put on the left, and then 2 times 11 would be your kind of end there. The 44 and the 22 are broken, so we don't need them anymore. So we call it the SOC method because it gives us these numbers here in that little SOC shape. Okay? And because the index on a square root is a 2 that we never write, right? We don't put the 2 there. It's the square root, but we don't put the 2 there. In the same way that we don't write 1x, or we don't write 1x to the first, or we don't write 1x over 1. Those are the assumed values for a coefficient. Assumed value for an exponent, assumed value for a denominator are 1s, because those are the lowest, most basic types of those. Well, there's no such thing as a 1th root. Okay, so the lowest, most basic root is a square root, so we don't write 2. Okay, so every year I've taught this, I have students freak out because they're like, but there's no index, or there's no little number, they usually say. Okay, what's it always been? Okay, you've known this for years, all right? What's it always been? So there's a 2 there, so we need groups of 2, right? The size of the group is 2, not we need groups of 2s. Okay, so we need things with 2 members. So this has 2 2s, so that 2 gets to come outside, all right? Because that's really a 4, and the square root of 4 is 2. But every group gives us 1 on the outside, and then we have that lonely 11 on the inside, and then the square root stays there, right? So the square root of 44 is equal to 2 times the square root of 11. Okay, so just, something you guys learned last semester. Okay? So we're going to apply that same idea to these bigger roots, except for now the group size is going to change, which is really what this is trying to get you guys to see. Okay? I want to look for sets that are equal to that particular group size. So when I look at this, this is telling me that I need groups of 3. Okay, not groups of 3s, groups of 3, or group size of 3. Okay. So as we go to break down 135, right? Well, that's not divisible by 2. Let's check to see if it's divisible by 3. So you might need a calculator just to do some division. 135 divided by 3 is 45. So, and then of course that's 3 times 15, which is 3 times 5. So there's our SOC. We want to look for groups of 3. So we happen to have 3 3s. Okay, so it's just a coincidence. Okay, so we have 3 3s, and then we have a lonely 5. So the group gets to come outside as one of those, because 3 times 3 times 3 is 27. The cube root of 27 is 3. Okay. 5 stays under. Okay, but under what? Make sure you put cube root. Our Lord. Okay, one of the more common mistakes students make with this is that they forget to put the index back on the root. Okay? This does not equal 3 square roots of 5. Okay? These two numbers are not the same thing. Okay? It has to be a cube root, not a square root. So you can't do that. Okay? You might notice the way I wrote that, there's a little bit of space between the green 3 and then the radical. That is something you guys want to consider as your handwriting here. Okay? if you get these things too squished together, it can be kind of hard to tell what's what. Okay, especially if you let this happen. Okay, that's especially bad, where that index drifted off and looks more like an exponent now than anything. Okay, so if you get things too squished together, Aiden, I might be talking to you. Okay, that it gets hard to tell what's what. Okay, so you're going to see me putting space in here. And I would ask you guys to do the same thing. Give yourself space there. Because really what's happening here, there is multiplication. Okay? It's 3 times this cube root of 5. We don't put those little dots there. You certainly can if you want to, but we don't. Okay, just like we don't put 3 dot x, we just say 3x. Okay? But especially you want to make sure you guys are not doing this. That's bad. So make sure your index stays right there in the little crook of the radical, pushed up against the radical. Give yourself space away from that coefficient. Okay? Check the chat here. Why not put 27 on the outside, Aiden? Because remember, we're cube rooting the 27. Right? If I said what's the square root of 9, I wouldn't say it's 9, right? Square root of 9 is 3. So because that 9 gave me 2 3s, I pair them up and then I get to bring that 1 3 out, right? Same way that, this 4 is actually a 2, because the square root of 4 is 2. So this is this 27 that I'm cube rooting, which gives me 3. Yes, I did say the double 3 was a coincidence, that this is, I needed a group of 3 and it was 3 3s, Brian. Same thing here, that I needed a group of 2s and I happen to have 2 2s. That's just a coincidence. Okay, let's try again with a bigger one, right? So here, what do we need, right? So first thing to pay attention to is, what's my group size? Yeah, so group size is 5, so we need 5 of something in order to come outside, okay? So we break 972 down. Of course, that's divisible by 2. 972 divided by 2 is 486, which is also divisible by 2 times 243. That's no longer divisible by 2. But 3 times 81, which is 3 times 27, which is 3 times 9, which is 3 times 3. Okay, a couple 2s and a whole bunch of 3s. All right, so we got a big old long sock here, right? All those numbers on the right side are done. We don't care about those. Okay? If you want to sit there and cross them out, you certainly can. I need 5 of something in order to make a group. Luckily, we have 5 3s. So if you're in a group, you get to go outside. That's not a 5. Why did I write a 5 there? If you're in a group, you get to go outside. That's one group of 3s gives me 1 3. Give myself space before I write my radical. And I need to make sure I put 5th root. Okay, so make sure you put your index there. And then I look at what's lonely. Right? Lonely 2 and a lonely 2. Well, they're both going back in. Right? Since they didn't get broken up, they were 4. Right? Just like before. It's all, same thing that happened when you guys did square roots. Anything that goes back inside multiplies back together. So 3 times this 5th root of 4. Okay, 3 5th roots of 4. So do want to make sure you guys can say this stuff. Okay, that's the 5th root of 972. And it's not the 5 root, it's the 5th root of 972. And then you end up with 3 5th roots of 4, or 3 times the 5th root of 4. Okay? So as far as just saying that stuff. Yeah, right, kind of. The 2 2s aren't a group because it's not a big enough group. In order to go outside, you have to be in a group of 5. Like there's some monster out there that won't eat you if you're in groups of 5, right? But as soon as that, if there'd been an extra 3, then it, also would have not been groups. That's it. Brings me to an example somebody asked about in first hour, so I'll go ahead and do that one again. If I do like the cube root of 80, okay. So cube root of 80, just want to break that down, which is 2 times 40, 2 times 20, 2 times 10, 2 times 5. Our group size needs to be 3. So we do have a group of 3 2s. Then we have a lonely 2 and a lonely 5. So that would equal, so my group of 2s gives me a 2 on the outside. Still have my cube root. And then the 2 and the 5 go back together as a 10. Okay, so any extra numbers, right, that are still too many for a group, they just get sent back inside. And only groups of 3 gets to come out on this one. The last thing I would do if I were you guys would always be to check to see if you put your index back on. Yeah, again, leave space here. Yeah, it's 2 times the cube root of 10. If you want to, you certainly can put that little dot there. Okay, nothing wrong with that. But I just ask you guys to leave space. And it's not a mile of space either. It's just a little bit of space. And just to be clear. Okay. So maybe you guys a couple to do on your own, but there's no way for you to type these easily. Okay. So what I would ask you guys to do as far as typing, I would say 2, all right, and then Shift 8 is your multiplication symbol. And I'm going to have you guys write this way. So 2 times the 3 root of 10, which I definitely don't want you guys saying 3 root, but there's no other easy way to type it. This one would be 3 times the 5 root of 4. Okay. So give you guys a couple to do, and then type me back your answers in the chat using this. Okay. I'll bring this over. You have an example there. All right, try these 2. Send your answers back in the chat. You're close, Sophia. I think you can see one little thing off. Good, Aiden. Not quite, Cornelia. You're close. Sophia, yours is mainly a typing issue. Good, June. Good, Mason. No, Aiden, that's not right on the second one. You're close though, Aiden. Yes, Aiden, good. Good, Kyla. Yeah, you're good, Aiden. Good, Brian. Good, June. You good, Jordan? You're sorting. Sure, Jubal. Yeah, I guess so. Interesting way to type that. So 2 and 24, 2 and 12, 2 and 6, 2 and 3. On groups of 4. So 4 twos will come out. Only 3. And I want to make sure I put a 4th root back on. So 4 4th roots of 3 on the first one. It's 2 times 27, which is 3 times 9, which is 3 times 3. On groups of 3, 3 threes, lonely 2, and make sure I put a cube root on the 2. So 3 cube roots of 2. Are you good, Sophia? Anybody, anything there? We're gonna just kind of add the next little wrinkle to it, so make sure before we move on. Good, Braylon. Cool. All right. So adding, subtracting roots, you might want to write down this part. Yeah. Really, this is the big deal. Like that, in order to do this, the index, which is that, those two things have to be the same, and then the radicands also have to be the same. If those two things match, then you can just do the math the way it kind of says it is. Okay, so this would essentially be like, if they match, this problem is essentially the same thing as 7x minus x. Okay, it's just like terms essentially. The things have to be the same in order for me to subtract or add them. Okay. So when they match, you just can do the way it is. 7 fifth roots of 12 minus 1 fifth root of 12, right? It is a 1 fifth root of 12. It'll just be 7 minus 1, which is 6, of course. And then the fifth root of 12 doesn't change. Okay. So I have 7 of something minus 1 of something. That means I have 6 of that thing. The thing doesn't change. That was definitely something I remember in my math life. That was one of the big things that really helped me understand how to do like fractional math or math like this. Is that in variable math, it's just that this is just a thing, okay, and the thing doesn't change when I add, subtract amounts of them. Okay, 7x's plus 1x is just 8x's, or 7 pumpkins plus 12 pumpkins is just 19 pumpkins. It's the number of the things that changes, but the thing itself is just staying the same. Okay, so we're doing adding, subtracting. Those things will stay the same, but they also have to be the same. So when I go look at the next one, they both have the same index. Right, so that's good, but their radicands are different. That's not okay. So unless I can get those to be the same, I can't do this problem. If your indexes are different, there's pretty much nothing we can do to change that. Okay, so if those were ever different, there's really nothing you can do. We can manipulate what's underneath the radical, by simplifying it. So we do have a way of easily changing the radicand. Okay? Changing the index is not something that we're going to be up to, so I wouldn't worry about it. Okay? This is essentially like if I said, hey, what's 7/5 plus 2/15? Right? There's something I would need to do first before I can do that because I don't have like terms. Okay? So that's essentially what we need to do. We need to simplify what's underneath the radical first before we're going to do this. So 81, of course, is 3 times 27, which is 3 times 9, which is 3 times 3. So we said we wanted a group of 3, so there are 3 3s. There's also a lonely 3. Definitely one of the more common mistakes people make with this type of problem is they forget about the 4 that was in the front. And this is, again, something you guys have done before with square roots. This is not a brand new skill. Okay, so that 4 drops down. The 3 also comes out. Then I have my radical still, so cube root. And then that 3 that was left over. Okay? But just like before, right? It's 4 times the cube root of 81, so it's 4 times 3. Okay? So that's really 12 cube roots of 3. Then I have a minus sign here. So just don't lose track of that coefficient that was out front already. Then I'm going to go look at the 24, see what I can do to that. So 2 times 12, 2 times 6, 2 times 3. So we need a group of 3. We've got 3 2s, so 2 gets to come out. Still have a cube root. We've got a lonely 3. That 3 stays in. And there's nothing I need to do here. That's just 2 cube roots of 3, so I'm just going to bring that down. Okay. And so what I look at now is, are these things all the same, right? Is everything the same about those? So now that those match, now we can do this math. 12 minus 2, of course, is 10. And then those cube roots of 3 just come down. 12 cube roots of 3 minus 2 cube roots of 3 is 10 cube roots of 3. The thing doesn't change, just how many of them we have changes. Once it's simplified, it's not changing anymore. And if I had to type that, I would say 10 times 3 root 3. Okay. If you guys are ready, I'll have you guys try a couple on your own. Anything you guys want me to talk about before I send you off to do one? All right, you guys try these 2. Send me back what you get. So, the first one should have been pretty straightforward. The indexes and the radicands are the same already, so we just need to take our 1 of something plus 3 of something to get 4 of that thing. Second one, the indexes are the same, and you can just make sure you guys are paying attention, seeing that most of you got that. The index was 2 there, but the radicands are different, so we need to look at what we can do with simplifying. Of course, 5 can't be broken down, but 20 can, so we need to work on that 20. So 2 times 10 and 2 times 5. So we're looking for that group of 2 to come out. So that first thing's not going to change. 7 square root of 5 is not going to change. Minus 2, so bring that down. And then our group of 2's is going to come out. I get that lonely 5. All right, but of course all that's multiplying here, so that's really a 4. Right, so minus 4 square roots of 5. So 7 square roots of 5 minus 4 square roots of 5. And once these pieces are equal, we really can kind of just ignore them for a second. Say what's 7 of something minus 4 of something would just be equal to 3 of that thing. Okay. Yes, Aiden, good. Okay, so 3 square roots of 5 there on the end. Looked like a couple of you told me 5 square roots of 5. So I'm guessing that one of these 2's didn't make it down initially. Again, very common mistake. So just being careful with that coefficient that it doesn't drift away on you. Okay. Anything with the adding, subtracting you guys want to poke at before we move on to the last wrinkle? That's not what I meant to do. Okay, all right, so last thing here is variables. I don't know that you really need to write anything down here in the words. I think we've done stuff with variables with square roots before. We've done stuff with variables and the exponents. The same thing that we did with the exponent stuff. I really think the variable stuff in the end is easier than the number stuff, because variables don't hide what they are. They're, I see y to the 6th, it's 6 y's, and I see n to the 8th, it's 8 n's. Whereas I look at 64, and I'm like, what the heck is 64 made up of? So in the end, we still need to focus on how big are our groups, right? The groups need to be equal to the index. So I need groups of 3 here as I'm looking at things. There's really no other way to do this with the numbers besides breaking that number down. So that's the first thing I'm gonna do is just break that 64 down. And I do need to make sure you guys are showing your work as you're doing this, that you should not just be ending up with an answer, some magical answer. Okay. So breaking that 64 down, it's got a whole bunch of 2's in it. All right, and again, why I like variables, there's just y to the 6th means 6 y's multiplying each other. Okay. It's pretty straightforward. So as I go looking for groups, all right, I've got one group of 3 2's, and I've got another group of 3 2's. I don't have any lonely 2's. And I got one group of 3 y's. I've got another group of 3 y's. I don't have any lonely y's. Remember, every group gives me one of those things, right, Aiden? So that I get a 2 out of there. I get another 2 out of there. I get a y, and I get a y. All right, each group is just giving me 1. Well, 2 times 2 times y times y is 4y squared.
So for each group of 3, you get 1. All right.
Because that group of 3 2's is really an 8, and the cube root of 8 is 2. And a group of y's is a y cubed, and the cube root of y cubed is just y. Right? So just the easy way for me to say though is each group gives me 1. Right? So I have 2 groups of 2, so I get 2 2's. I have 2 groups of y's, so I get 2 y's. Each group gives me 1. Okay? Well, right, there was no radical, right? Because we didn't have anything lonely. So technically this is what's called a perfect cube. 64 y to the 6th is a perfect cube. So that when we're done cube rooting it, we don't have a cube root anymore. Just like if I said, what's a square root of 25? It's just 5. It's not 5 square roots of something something. Okay? So you don't need to know this, but just let you know it is a perfect cube. That's why it came out perfectly. Okay. So if there's nothing lonely, if there's nothing left over, you don't need a radical in your answer. Okay? There's nothing saying that we have to have a radical in our answer. There's no reason for it here, so we don't need it. Okay. So if that's something you feel like you need to write down, though, right? If everything goes outside, then we don't need an inside, right? If we're using that language, right? This group goes outside, this group goes outside. Well, they all went outside, so we don't need an inside anymore. Okay? So that's why there's no radical there. Right? And that's okay. It happens sometimes. Fraction ones, I see the weirdest mistake on here year after year, and I don't understand why. Sometimes I can kind of get why people make the mistake they do, but here I just don't understand. The fourth root of m to the fourth over n to the eighth. So, of course, m to the fourth is just m times m times m times m, and then got 8 n's on the bottom. Okay. Yeah, but what matters here is how big of a group we need. We need groups of 4. So I've got one group of 4 m's, got a group of 4 n's, got another group of 4 n's, right? So I have one m, right? And then it's over 2 n's, right? N and an n. It should be pretty simple. That's just m over n squared. I don't know, every year I've had students that push the n to the top for whatever reason. They write mn squared, and I really don't know why. It's a fraction. Why is it not staying a fraction? Every year I have multiple students that do that, and I don't understand that mistake. So don't do that. Okay. Yeah, that one was a perfect 4th power, right? So we don't have a radical there left over. So these are perfect ones. We'll see some imperfect ones here next. Not really going to change my process here as we go to the messier ones. It's going to be the same thing. We're going to sock out the number. We're going to write out our variables. Just go circling groups. So, okay. Does anybody need more time here? Only I warning here is that, like the second example over there is a really big problem. You guys won't have to worry about problems like this big on your own. I just wanted to show you what it would look like. And it being big doesn't make it difficult. It's just kind of annoying because you have to write a whole bunch, but it's still really easy. So look at the cube root of 14, x to the 7th, m to the 4th, y to the 10th. It kind of annoys me that they're not in alphabetical order. I don't know why the problem was written that way, but there it is. Normally I would write the problem in alphabetical order. But, 14 is just 2 times 7. Not much for me to do there. X to the 7th is just 7 x's. Just watch your counting. M to the 4th. Y to the 10th. So writing out 10 y's. Just be careful again. It's not difficult. It's just kind of annoying to have to write that many y's. Then we need to go looking for groups of 3, right? So our index is 3, so we'll go looking for groups 3. I don't have 3 2s or 3 7s, so those guys are both lonely. 3 x's. I've got 3 more x's. Then I've got a lonely x. I got 3 m's. Then I've got a lonely m. Got 3 y's, 3 y's, 3 y's, and I've got a lonely y. There is a faster way to do this. I don't really want to teach you guys it because I've had students take my little shortcut and then do it wrong. So if you feel like you see a pattern to this, a faster way to do it kind of in your head, feel free to check with me and use it. But otherwise, just kind of write everything out and make your groups. It's pretty straightforward. So, and this next thing that I'm going to write, I don't necessarily need you guys to write all the time. I'm going to write it for you guys to see how it works. And then again, there's a way to just kind of move past it straight into the answer, which I'd be okay with. You guys can do that. but definitely the first time I do this with you, I want to write it all out for you. Right, so we always want to focus on our groups first, and so every time we get a group, we get to bring one. So I have one X and another X, and I've got a group of M's, and I've got a group of Y's, I've got another group of Y's, I've got another group of Y's. Right? Every group gives me one. I give myself a little space because I'm writing my radical, so my cube root. Give myself, some space underneath my radical too because I got lots of stuff to write. We had a lonely 2, a lonely 7, a lonely X, a lonely M, and a lonely Y. Right? And all this stuff is multiplying. Right? There's multiplication everywhere. If you want those dots, you can do that. So I don't necessarily need you guys to write it all out like that. If you need to for yourself, go for it. Okay? But really what I'd like you guys to see is like, oh, I have 2 X's. That's an X squared. Oh, I have 1 M. That's an M. Hey, I've got 3 groups of Y's. That's a Y cubed. Right? And definitely you don't want to squish your radical right up here. Right? That's not a good look. Yeah, so give yourself a little space there if you want that little dot. Cube root. 2 times 7 is 14. 1x, 1m, and 1y. 14xmy. All squished together under the radical. So that'll be our final answer. So if you guys want to go from here to here, I'm fine with that. Okay? But I am not okay if you go from here to there. That's not okay. Will not accept magical answers from you guys. I want to see where your stuff's coming from and how you're breaking it down. Okay? You guys okay with that one? I'm ready to move on if you are. Again, this was really a very big problem. That purely, when I say it's just purely like a big writing problem. It's math itself is really easy. Okay. So breaking down 192, it's 2 times 96, which is 2 times 48, which is 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. And I've got to write out 8 W's. 12 H's. And 10 Y's. Okay. Again, there is a faster way to do this in your head. If you feel like you see it, if you want to check with me, please let me know. Otherwise, just do it the concrete way, which is where you write everything out and go circling. So we need groups of 6. Our biggest index that we've seen, right? So groups of 6. So we have here 1, 2, 3, 4, 5, 6. So we have 6 2's. Only 3 though. Oops. 6 W's. 2 leftover W's. Oops, I meant to be a different color. I've got 6 H's here. I've got 6 more H's. No leftovers. And then 6 Y's with 4 leftovers. So a 2 gets to come. I have 1 group of 2's. I have 1 group of W's. And I don't necessarily need you guys writing it out all like this if you don't want to. 2 groups of H's. 1 group of Y's. So those are all my groups that get to go out. A bit of space. 6th root. Give myself space there. And what was lonely? Add a 3. Add a W. Add another W. No H's. and y, 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 y. Okay? So if you need to write it out like that, you can. Or if you feel like you can go straight to the answer, 2w h squared y, 6th root 3w squared y to the 4th. You can go straight to there. I'm happy with that. Okay, so if you can go from this to there, I'm cool with that. Okay, you don't need to do the middle stuff. Anything weird there? Pretty much you always want to start with the smallest number, right? And half of all numbers are divisible by 2, so it's always a good place to start. Right? I mean, if it's not even, then you can't divide by 2. So 3 would be the next thing I would try. And then if not 3, then 5 is always pretty easy to see if it's divisible by 5 or not. So yeah, but I always try 2 first if I can, right? If it's even. The sock method asks you to take out the smallest number you have first. Always the smallest, right? Put that on the left. I'm just going to show you this one last one, then will be good. Just that you guys don't need to, as long as the index, which is here, which would be a 2, as long as those are the same, right, which they are, and the radicands are the same, right, those are both the same, okay, then we can just do what it says, right? Just take that thing as it's, it's a thing. I have 3 things minus 4 things, just give me -1 of those things. The thing itself doesn't change. Right? -1 xy is really the same thing as -1 square root of xy. Same thing as negative square root of xy. That would be the easiest way to write it, simplest way to write it. So just throwing in variables there doesn't change that process. That you just need to make them the same. If they aren't, I don't think you guys have a lot of problems. Like, it's not something we spend a lot of time doing. Is the problem like that? But just so you know, it doesn't change the process at all. Okay.